you all for coming. Today, I'm going to be talking about CAD. It's going to be great. We're going to have lots of fun. So this is going to be a really informal presentation. Please just let me know if you have any questions. I love questions. I also have a lot of fun stories, so if you ask me questions, I'll be able to answer them. So yeah, do you want to go to the next one? So a little bit about me. I'm going to be a senior this year. I do CAD, and I'm also part of Outreach and Awards. And I just stuck this in as a disclaimer. I'm not a professional mechanical engineer. I'm not a multi-decade FRC mentor. I also don't know everything. So this presentation is mostly about what I've experienced from being on ISM1 and doing CAD. I'm also never done learning about CAD and design. It's such a wide field. There's so many more things to learn about it. The software has so many things. The design, just learning design, there's so many new things you can learn. So just take me, yeah. Okay, so the first thing we're going to talk about is what the difference is between CAD and design. So I know a lot of teams kind of group those into the same thing. Your CAD lead is the same as your design lead, but they're actually quite different. So CAD is a software. What we use on our team is Solidworks. Some of you probably use different things, like Inventor, Fusion. For today's presentation, it doesn't really matter what you use. The principle behind it is all the same. But CAD is a tool, so it's something that you use to accomplish something, right? But then when you're designing something, you're creating something for a specific purpose. You have something that you want to accomplish, and you're trying to do it. So you're building an arm to put something on the scale. You're building intakes to be able to intake a cube at X position, right? And then often when you're designing, you use physics, mathematics to optimize functionality. You want to know how something is going to work when it's actually on the field. So today we're going to be talking about how we use CAD software to optimize design. So how do we use the CAD software as we go through the build season to be able to optimize and increase functionality, to predict what's going to happen when we actually design a mechanism and then put it out into the field. So any questions about that? Oh, just because I'm curious, how many of you guys use SolidWorks? Okay, that's like most. Any Inventor or Fusion? Okay, that's totally fine. You'll still understand. Okay, so what happens on day one of build season? So you get the game. You're probably very excited. Sometimes you're probably a little scared. But what we do is we start brainstorming potential strategies. So what do we want to be able to do? Do we want to be able to place on the scale? Do we want to be able to place on the switch? What kind of mechanisms do we want to build that will accomplish them? So we'll always come up with some goals. So to maximize the amount of points that we can accomplish, what kind of strategies do we want to deploy? Like, do we want to be running defense? Do we want to be doing a vault, switch, to scale? And then how are we going to build mechanisms to accomplish those goals? So are we going to build an elevator? Are we going to build a double-jointed arm? What's going to happen, right? So then we want to know if something will work. Because you can say, oh, I'm going to build like a 10-jointed arm that's in the game animation, but you don't really know if that's going to work. So then the first thing you want to think about is what your design constraints are. So what is the game constraints? How big can your robot be? How tall can it be? So how are you constrained there? And then the second one is, how is your team constrained? So what kind of resources do you have? How many people do you have working on CAD? How much experience and like how much do you know? What is your manpower essentially? So a good example I always make here is we build an off-season robot called the third robot, and it's always very different from the season robot because our off-season robot doesn't have any mentor involvement. It's completely student-run. So the resources and the team constraints for the third robot is very different from what we can allow for ourselves for during the season. If that makes sense. And then you also want to think about, back to your original strategies, what do you want your robot to be able to do? So you have strategies. Maybe you want to be able to place on the switch and do the vault, or maybe you want to be able to do the scale and defense. So what kind of mechanisms are you going to be building? And are those going to work to accomplish that goal that you set for yourself? Okay. So in order to accomplish those goals, you want to ask yourself some specific questions. So you probably accomplish this doing either prototyping or doing some CAD modeling, and I'll talk about those a little bit later. But you want to ask specific questions. You want to know exactly how you're going to solve your problem. So you don't want to. You're not just prototyping just because. You're also not going to prototype your whole robot. You're prototyping specific aspects of your robot to be able to solve specific questions. So what I have here is, how tall does the arm need to be to stack too high on a losing scale? That's a very specific question. You have a goal. You want to stack too high on a losing scale. Okay, so how are you going to do that? Where are you going to put your wheels on your intake so the cube doesn't get stuck? So if you attended our overview, you would know that one of our main goals was to be able to intake the cube in whatever position. So how are we going to build a mechanism that accomplishes that? And then what kind of material would grab the cube well? So we were testing a bunch of different materials to grab the cube. So how are we going to do that too? Okay, so then how are we going to answer these questions, right? You have questions. You don't know how you're going to build an arm. You don't know how tall it's going to be. You don't know what your intake's going to look like, right? So now you want to start solving these questions. So the first thing there's two different ways that you can start. Week 1 of build season, you have to go really broad. You don't really know what your robot's going to look like. You kind of know what you want. So then prototyping is more like real life situations. There's things that happen on the field that you can't really account for in CAD. So like the carpet, that one's always a big one. You can't model a carpet in CAD. You can't model the friction that the cube has across the carpet. So you always want to be prototyping something that allows you to address those issues. So this is kind of like what happens in real life. You're trying to simulate what's going to happen on the field, but then you also have questions that you can answer in CAD. So, for example, how tall does our arm need to be? You don't need to build an arm prototype to answer that question. You can model that in, and then model the different segments. And I'll talk about a little bit more about how we do this next. Okay, so to answer those questions that we can solve in CAD, we do something called Crayola CAD. And then it's called Crayola CAD because you can liken it to drawing with crayons. When you're drawing with crayons, it's not exactly the most specific thing. You don't exactly know how big that part is going to be and like how big that part is going to be, but you can approximate. And you only have what you care about. So it's big blocks, it's sketches and representations, and you're trying to solve, like I said, you're trying to solve a specific question. You're trying to find an answer to something. So this would either be how long is my arm going to be? So maybe you have one segment for the distal, one length of the arm, and then you have another segment for another length of the arm, and okay, is that tall enough, right? You are trying to understand the pros and cons of different designs. So is this feasible? Is this going to be possible? Can we do it with the resources that we have? How is this mechanism going to interact with the rest of the robot? So where is my intakes going to go? Where are my arms going to go? Is it all going to fit together? Am I going to be able to package this right? And then you also want to think about what necessary components will I need. So then, am I going to be able to accomplish this with the components that are available to me? So, okay. So then, this is an example. This is from our 2017 intake. We had tubes that came out and intake the balls, and then came back in. So 2017 was with the bright green balls, and then you intake them into your robot. So then this was where we were packaging. We knew that we wanted an arm. So then where are all the components going to be so that we can bring the balls in, right? So the pink line right here, that's the actual intake. So that's the part that comes out. And then the green ones, those are the balls. So it models the path of the balls as it flows into the robot. And then up there you can see all the belts and the pulleys that we had to model in because we wanted to know if it would fit together, if everything was going to work. Okay, so then this is an example that I've been giving very often. How tall does our arm need to be to reach the scale? So if you look at this right here, it's obviously not made out of carbon fiber. It basically doesn't have that much in it, but it has what we care about. It has the length of the arms, and we know that it can reach the scale. So yay, we've accomplished our goals, right? We know how long our arm segments are going to be. Okay, so what's next, right? So then over there you can see the sketch that we used to accomplish this. We have the path of the arm, and then seeing that the line up there is our goal. So how are we going to configure the different lengths of the arm so that we can reach that goal? And you can also see that in its packaged form, it's underneath that middle line, which is the robot size constraints. So you have multiple constraints that you're working with, and you also have one final goal. So you're trying to accomplish that final goal through modeling these rough sketches in CAD and these rough blocks. Does that make sense? I'm going to stop right here and ask if there's any questions. Okay, perfect. So this is another great example. This is mostly a packaging example. So in 2017, which was Steamworks, we actually put a large 23-inch diameter serializer that sorted the balls in the middle of our robot. So where is everything else going to go, right? You have this large circle in there, but where are we going to put our transmissions? Where is our battery going to go? So where's the intake going to go, and how is it all going to work together as a whole robot? You want to be thinking of how the intake is going to interact with the serializer, because it's going to go from the intake to the serializer. So where is everything going to go? How is it all going to fit in? And you can see that that's obviously not a robot, but you have what you care about. You have the size of the serializer, and you have a model of all the other parts that you care about. So you have your intake, you have your drive phase, and then you have the little shooter. Okay, great. So maybe by now you're in week 1, week 2 of build season. You know kind of what mechanisms you want. You know how they kind of fit in with the whole robot. You kind of have their basic constraints in. So okay, what's next, right? So then an important thing that we do is something called geometry. So what is geometry? Basically, you have your mechanism planned out on a large scale. You know probably how big it is, how tall it is, but you don't really know how it's going to work. So geometry is more detailed planning. You have 2D sketches to show all the components that you care about. So a good example I give is a gearbox. You know you want a gearbox. You know kind of what speeds it's going to have. You know where it's going to go on the robot. So what's next, right? Where are our motors going to go? Where are our gears going to go? And how are we going to plan this out so it's going to be packaged efficiently and so that it works? So you want to do relations and dimensions. So you make Solidworks relations and dimensions, and you dimension to all the components that you have and that you care about. So then in the gearbox example, something that you might not care about as much as like lightning or pocketing, but something that you do care about is where your motors are going to go. And then you probably want to do some kind of math and physics to know if the gearbox or whatever mechanism you have is going to work. Probably depends. So yeah, any questions? You go back. Questions? And I'm going to go into more specific examples later. Okay, cool. So how does geometry work with Crayola CAD, right? So I talked about Crayola CAD. I talked a little bit about prototyping, but how do they all work together to figure out whether a design is effective? So with Crayola CAD and prototyping, you kind of figure out if a mechanism is going to work. You know, with prototyping, you know that, okay, if I make an intake that's about this big and has about these constraints and dimensions, well, okay, it's going to work, right? It intakes the cube the way we want it to. And then with Crayola CAD, you say, oh, if we stick the serializer in the middle of the robot, where is all our other stuff going to go? Like, if we put a transmission right there, is it going to fit? Is the serializer going to run into it? Is that going to work? And then with geometry, you're solving the more specific like hows of a mechanism. You're solving if it's going to, well, let's go to the next. Okay, so this is the 2017 intake example again. So how far will the intake need to extend? What will the roller geometry look like? So in the previous example of the intake, I kind of showed how it was packaging. But then with this one, you know that you want an intake that does that telescoping motion, right? Okay, so what's next, right? You know that you have rollers, so you're kind of planning out how is our intake going to stow? Like, where is it going to be when it's in that stow position? And then when it's out, how is it going to intake the balls? So where are we going to put the roller so that it can intake the ball effectively? And a big thing when we were doing this design was that dead space that you see right here, where when the ball gets into a certain position, you don't want it to not be touching any rollers. So configuring that was one of the most important parts of the sketch, figuring out how are we going to get the ball from there to there with it being driven the whole time. Okay, so here's another example. Here's the gearbox example that I gave before. So how are all the gears going to fit together in a gearbox, right? You have your tube. You know that it's going to, this is a drivetrain gearbox, by the way. You know that it's going to mount onto this tube right here. You know that you want it to drive that wheel right there. So, okay, where are our motors going to go? Where are we going to put our gears, right? So then you want a dimension to everything that you care about, like I said before. So right here, you have a motor. Well, I don't want my motors to run into my tube, so I'm going to stick a dimension right there so it's not going to run into my tube, right? I don't want my gears to run into my motor, so I'm going to put them right there, and they're going to be out of the way of the motors. I also want it to package efficiently, so I'm going to actually put the gear right there, and I'm going to check to make sure it's not going to run into the tube. I don't want the bearing. I want the bearing to be in the middle of the tube, and I don't want the bearing to be sticking out. So I'm going to stick a dimension to make sure that it doesn't do that. Does that make sense? Yes?
You have equations where you're labeling stuff. Why do you have that?
Okay, good question. So I actually probably should have mentioned this before, but SolidWorks actually does a lot of the math work for you. You're able to put in equations, and this solves a lot of your issues because you don't need to like pull out your calculator and be, oh, how big is this gear going to be? So with gears, do you know how to calculate gear diameters?
There's like tables, and that's always what I've used.
Okay, well there's actually a way that you can do it. So most of the gears that you buy on VexPro have something called DP, or they all have DP, but most of the gears that you buy on VexPro have 20 DP. And what that means is that for DP stands for diametric pitch. So for every 20 teeth on a gear, you have 1 inch diameter. And then, so then on a gear, you have something called pitch diameter, outer diameter, and inner diameter. If I drew something on the board, would it show up in the video?
Yeah.
Okay. Or you can stop then.
That video works.
Okay. Do I lift the thing up? Okay. So if you're looking at your gear, and your gear is like this, right? You have little extrusions. So you have your outer diameter, your pitch diameter, and your inner diameter. So your outer diameter goes across the top of your teeth, right? Your pitch diameter is actually this halfway, not really halfway, but it's this medium in between that you want your gears to mesh at. So you don't want it to overmesh, and you don't want it to undermesh, right? So your pitch diameter is, I think it's closer to the outside than the inside, but it's like the sweet spot that your gears are supposed to mesh at. And then you also have something called the inner diameter, which goes around the bottom. It's on the inside. So then these are all referencing the pitch diameter, but what diametric pitch means, back to my original point, is if you have something that has a 20 dp, it means that for every 20 teeth, you have 1 inch of your pitch diameter. So for example, a 20-tooth gear would have 1 inch pitch diameter. A 40-tooth gear would have 2 inches pitch diameter, and so on. So then what these equations are doing is that they're basically taking the gear numbers that you have and dividing them by 20, right? Because if you say, okay, sorry. So what you're saying is you're taking each tooth and dividing it by 20, and you're making an equation for it. That way it stays in the dimension. So for example, this is a 60-tooth gear. If I wanted to make a 58-tooth gear, I'd only have to go in and change the 58 number. And then that just makes a lot of your math really simple. It also prevents you from making errors, because if you say, oh, I want this gear to be 60-tooth, but then you actually model it in as 58, which I've actually done before, you're going to have an issue, because when you try to put the 60-tooth gear in, it's not going to fit, right? So then this just simplifies the process for you, because Solidworks is doing the math for you, and you're not making errors in your design through math. Does that answer your question? Yeah, okay, cool. Okay, and so I've kind of been going from less specific to more specific examples. So this is an example of the latch that was on our lift in 2018. So our lift flipped out, and then there was a latch holding it down for most of the match until it flipped out, right? So then this is a more specific one. When I was designing this, there was like, it was actually, I think it was week 6 of build season, but we basically already had a robot. We already had a drive base. I knew exactly where it was going to go. I knew where the latch was going to fit onto. So I have these constraints, and they're very specific constraints. You can't change how tall your drive base is. You can't really change where the lift is folding down. So I'm going to take those constraints and do something with that, right? So when I was doing this, there was a piston. This is piston geometry. So the latch, basically, the piston has something called a stroke length. So a piston is a pneumatics, and you're filling it with air. And then it's moving between 2 different positions. It has an arm that's moving between 2 different positions, so it's going from this position to this position. And it's a linear motion, right? So I'm modeling that in because that's what I care about. You can't change what your piston is. You can change what kind of piston you have, and you can change which piston you have, but once you picked a piston, you can't really change it. So that's what I care about, right? I know where my drive base is. I can't change that either. And I know where the latch is coming down. I can't change that either. So I'm taking those constraints, and I'm doing geometry to make sure that this is going to work, right? So right here, this is it fits onto a standoff, and that's how it holds the lift down. So then what I did was I actually modeled in a second standoff, and this kind of shows where the standoff is in the tilted position. So if you look at it sideways, that's what it's going to look like, and that just simplified the design a little bit for me. But having my constraints in there and dimensioning off of what I cared about, which was my constraints, made the entire CAD process a lot easier for me. And then later in the season, when we actually changed our lift, I was able to go back into this and just change how high it was. And then I didn't have to do anything else. And then it automatically saved everything for me, because this is like the overlying sketch that holds everything that I care about. So then if I just change how tall it is, then it's going to change everything in reference to what I care about. Yeah, any questions? Okay, cool. Okay, so then when you're making parts, there's something called multi-body parts that we use. So a lot of people have mixed opinions about multi-body parts, but I'm just going to talk about them, and then later I'll tell you what our challenges are with them. So for those of you who don't know, it's one single part. You're making one single part in whatever CAD software that you use. It doesn't matter. And then whatever extrudes bodies on top, you have something called bodies. So if you're making something like, I don't know, a gearbox, you're going to extrude your bottom plate, and then on top of that, you're going to extrude a circle. That's going to be one gear, right? And then you're going to extrude another circle, and that's going to be another gear. And each item is called a separate body. And then you have multiple bodies to make up your multi-body part. Does that make sense? And then this basically allows you, the biggest benefit of using multi-body parts is that there's no arbitrary dimensions. You have what you care about, and then everything is referenced on each other. So if you guys have ever made like complex assemblies, you know you're flipping back and forth between all the different parts, changing the dimensions, and then you have a lot of copy pasting going on. Sometimes you copy paste wrong, and that's always like a sad day. So this prevents that from happening because it's all one part, so everything references off each other, right? The biggest thing that we use it for is custom gearboxes, because you have one plate that's basically your underlying sketch. Everything references that one plate. And then you're able to extrude your gears on top of that, your circles that act as your gears, and then you're able to extrude your plates, and maybe if you have encoders, you put your encoders in there, and you see it all as one part. And then you say, oh, wait, I want this encoder to be, I don't know, 1 inch higher. So then you go back into your underlying sketch, and you change that 1 inch, so that it changes everything. It's very nice. And then there's no flipping back and forth between parts. You forget to put them in some parts, and then they're in other parts, and maybe you copy paste wrong. It's just always a mess. So it always helps us use them for custom gearboxes. But then there's also a trade-off, and I'll tell you guys about that later. I'm going to give an example. So this is our 2018 Arm Gearbox. We made it in one part. The gearbox plates are all in one part. So you can see it's a lot of features. I actually didn't snippet all of them, so this is like maybe 3/4 of them. So it's a lot of features. It's bodies upon bodies. So this is Solidworks. If you don't use Solidworks, I think it's similar in other softwares, but this is just, you can see at the top right here, this is your first body. And then you extrude your next body, and that's another body. And then as you're making extrusions, you can put features on it, like holes and contours. And then those affect the bodies, but they don't change the body count. Does that make sense? So each plate in here, there's like 4 plates. Each one is a separate body. Yeah. Okay, so if you go to the next one, I'll walk you guys through how we did this. So then in the Arm Gearbox, there's one underlying sketch. And then this is the sketch that shows where are all our arms going to go. We kind of know what our drive base looks like already. So how are we going to get around that? Because it kind of sits in the very back. There's wheels there. There's transmissions there. We don't want to run into any of that because that'd be a sad day, right? So we have the big circle right there is the sprocket that drives the proximal link, which is the closer link to the arm. And then these right here, those are the 2 transmission motors. And then there's a third one over there, but it's not close enough to the Arm Gearbox, so we don't really care about that, right? And then the wheel down there, we care about where that one is because we don't want our motors to be running into our wheels. So we want to model that in and dimension everything off that. So then based on what our constraints are, we're able to take the space that we have and optimize it to the best functionality. And packaging this was actually, I don't know, I'd say it was a lot of fun. It was also really hard. So you basically have the 2 motors down there. There's 2 motors down there for the proximal link. There's a motor up there. And then based on that, we have gear ratios that we already chose. So which gears are we going to use to get to that gear ratio, and how are they all going to fit in there? And this is our underlying sketch. This is like the first sketch on that long list of items. So then from there, we were like, okay, let's put the next one. Let's put a hanger gearbox in it. So we don't really have that much room. So how are we going to do this, right? So the original underlying sketch isn't going to change unless you want it to. So then based on that, you can optimize your space that you have down here, dimensioning off of the components that you had in the previous sketch. So your motor is going to be there. So I don't want this motor to run into that, so I'm going to make them 0.2 inches away, right? You know where your wheel is, so you don't want your motors down here to run into your wheel. And then if you go to the next one, I'll actually explain why we use multi-body parts. So it's a very big assembly. I mean, it's a very big part. There's a lot of things going on. So why did we do this, right? So as I mentioned before, we stuck the hanger gearbox into the arm about halfway through. We didn't really anticipate it to originally be on the arm, in the Arm Gearbox. So then we were thinking, okay, how are we going to fit this in, right? So there's two ways we could have gone around this. You could do a hanger gearbox that's made out of only gears, and then this would be from gear to gear to gear, right? So then you can see here we modeled that in. Obviously, it doesn't really fit because this is running into that, and we don't want our hanger gearbox to be running into our proximal sprocket, right? So then, and then the motors down here are running into the wheels. So then we said, okay, this isn't going to work, right? So then let's try again. Let's extrude another sketch right on top of this so we can compare the two really easily. So if you go to the next one. Here's the one that we have with gears and belts. So right here, you have your motors down here, and then you're able to go there with the belt, and then you come back down. So that makes your packaging a lot easier if you have belts. And then we said, okay, that's going to fit. It's going to work. And then we compared this to the previous one, and having two sketches that were right next to each other meant that we didn't need to flip back and forth. And since the underlying sketch, the sketch for the main gearbox with the proximal and the digital link, they were all the same, right? So we didn't need to copy paste it because you can copy paste sketches, but it doesn't automatically update. So then often at times we were saying, okay, we want this motor, the proximal motor, to be maybe just a smidge over. So then we could just go back into the original sketch and change that. And then that's the main reason why we use multi-body parts in the Arm Gearbox, because it was so easy to iterate upon, especially when you're doing tough packaging jobs like this, right? You have your main dimensions that you really care about, so how are you going to optimize everything else to fit with those constraints that you have, that you set for yourself originally? So then, now I'm going to talk about the challenges that we face. So the big thing about multi-body parts is that there's less arbitrary dimensions, and the turnaround time is really fast, right? You change one dimension and it changes the whole thing, instead of going through multiple parts and change them all. But then at the same time, you don't really want to, although it would have been nice, you don't want to model your whole robot in a multi-body part, because you could, but you shouldn't, because the bigger parts get, the longer they take to load. So then if you end up breaking something really early up on your feature tree, you guys all know what that is? Yeah, I'm just going to go over it. Can you go back like to the slide? So this is called your feature tree. It's kind of like a, I don't know, it's a tree. It basically goes chronologically. So these are the first parts that you make, and then as you go down, they reference, each part references parts that are, each feature references features that are above it, but not below it. So if you break something really early up on your feature tree, you can break everything else. And you can imagine in parts that are this big, it gets really annoying if you break maybe the top level sketch and then everything else breaks. So then if you're making a whole robot out of a multi-body part, can you go back to that slide? If you make your whole robot out of a multi-body part and you break your first sketch, you might have to go through and redo a lot of your parts. And they can take forever to load, so I'll give a couple examples later, but it kind of takes you have to know when to use them and when not to use them. And I think I'm still learning this, I think our team is still learning this, because there's ways that you can use it to your benefit, and then there's also ways that you can use them to your disadvantage. Wait, before we go on to the next one, does anyone have any questions about multi-body parts, about geometry? Okay. Cool. So I'm going to talk briefly about the parts management and the parts library, because this is accessibility is in the title of the name of the presentation. So we have a parts library that is available to every single student who's doing CAD. And COTS parts stands for custom off-the-shelf parts. And then these are parts that you can buy on McMaster, on VexPro, on WCP. And then it's really annoying to have to go download the part and bring that into the folder every single time you're making, say, a gearbox or maybe an arm. Downloading all the parts individually and pulling them into the folder is really annoying. And also, if everybody's parts are in different folders, when you try to open someone else's, if their gears are in their downloads folder, Solidworks isn't going to find those same gears in your downloads folder, so you're going to have a problem, right? So what we do is we have a folder called the parts library, and that shows all the common parts that you can buy from McMaster, from VexPro. So this would be like bearings, gears, sprockets, motors, and then this keeps everyone's COTS parts in the same place, so that if you open someone else's gearbox, it's not going to break everything because their gears are in their downloads folder or something, right? So then, probably the more important aspect of accessibility is the parts list. So 971 has a parts list that we update with every single part that we make in CAD. So that spacer has a part number. The Arm Gearbox plates has a part number. So basically, each part has a part number, and then you track that part throughout the entire process. So when it's being CAD'ed, you know what it's being CAD'ed. And then when it moves to drawings, and cam and routering, and then when it's kitted and put it into the robot, you know where that part is. And this is really beneficial to us because a lot of our robots have 300, 400 parts. How are we going to keep track of them all? You have that one space that's really essential to your, I don't know, your mechanism, but if you can't find it and you don't put it in, your mechanism might not work the way you want it to. So this helps us keep track of all our parts. And then we also have custom properties that we set ourselves. So Solidworks allows you to set properties for every single part that you make. We actually have our own list, so I think the default Solidworks ones aren't going to be these ones, but it allows us to write in the part name, the part number, and the material, and all these properties. And then this, in a robot that has 300, 400 parts, going through and counting every single 1032 volt would be really annoying. And going through and counting all your gears, that's really annoying. So it generates a BOM, and then the BOM is generated from the custom properties, and from there we're able to, it automatically tells us how many spacers we need to buy, how many bolts we need to buy, and that makes our lives a lot easier. Okay, next. Okay, so probably the most important part is iteration, right? You can make mechanisms, but they might not always work the first time. So you want to be able to use SolidWorks or whatever CAD software that you use to optimize your design so you can iterate and go back and change them, right? And I talked a little bit about this with geometry, with multibody parts, but there's an underlying principle that's everything needs to have a reason. You're not making a feature because you want to, right? You're making a feature because it's going to help your design. Yeah, so you don't just make features to make them. And a fun story about this is when I first started doing CAD, I used to fill in my holes with plastic extrudes because I didn't want to go back and delete the hole. And then when you go back and you try to change the underlying sketch, it's going to break everything. And then you basically have to start over. So you want to make features because they're going to help your design, not just because they're convenient for you at the time, right? So then a good way that you can accomplish this, I talked a little bit about this before, is to do a top-level sketch. This is a sketch that has everything you care about, so all your constraints, all your motors, all your components, whatever is in your part, right? And then you want to dimension not arbitrarily, but what you care about. So you're not making this dimension 1.5736 inches just cuts. You're making it because it has a reason, and round numbers are always better. But the big thing is that you want to make it easy for you to go back and modify the design. And I'll go through a couple examples. Okay, so here's a simple example, right? This is a shaft. They're not really the same shaft, but you kind of get the point across. This one here is an underlying sketch, so it has everything that you want, right? You know you want a snap ring, so you dimension that in here. You know you want, this is a shifter shaft, so you know you want your gears to fit in right there, so you're going to dimension that there. You know you want a bearing at the end, so you're going to put that in there too. But then in the next one, which I actually just did, the way that I did it was I had a hex shaft and then I just extruded it and then I cut features out of it as to what I wanted to. And yeah, maybe it was more convenient. It probably took me less time than this one did. But then what if I want to change how wide my gearbox is? Then I have to go through and I have to modify every single part right there. And then also, what if the gearbox plates happen to be a really arbitrary number apart? Then you have to copy paste that number and paste that into every single feature that you have. And that's just really annoying. And you're probably, maybe, I don't know, maybe you're really good at copy pasting, but I think I would copy paste wrong. So you want to prevent that from happening, because then you'd end up with parts that don't align, and sometimes you don't catch that in CAD because everything is so dense. So then when you're manufacturing stuff and you're trying to put this together, you're like, oh, this shaft doesn't fit between these two gearboxes because I didn't make a top-level sketch that dimensioned everything. But then in this one, if you want to change how wide your gearbox is, you change one number, and everything changes to match that. And that's a lot more convenient for you, because if you have a shaft, obviously that's not a really complicated shaft, but if you have a shaft that is more complex, then it would be really annoying to have to go back and remanufacture that and redesign that if you happen to not have done it correctly. So, yeah. Okay, so here's a less simple example. This is a 2017 turret. So our 2017 robot had a shooter that rotated. So when we were doing this, we knew basically how wide our shooter was. So then we wanted to, from there we said, okay, I know how big my shooter is, so how am I supposed to get dimensions, and how am I supposed to do everything so that it fits with the rest of the robot, right? So then you have you know you want a motor, you know you want to drive the shooter in some way, the turret in some way. So then you make an underlying sketch with everything that you care about. You care about where the gearbox is relatively. You care that it's not running into the shooter, so you put that in, and then you care about where it's being driven. And then from this is your underlying sketch. From this, you're able to go into there and extrude your features, right? You're able to extrude your gearbox plates, you're able to put in your standoffs, you're able to put in your encoders based on what you have in here. Because this is what you care about, this is what you don't want to change, or this is what you want to be the most important part of your design. Any questions? Okay. So, okay, I'm going to say something cheesy about iteration. All 9 similar mechanisms go through iteration. I know a lot of our designs look clean. They look kind of, I don't know, I think the arm is kind of flashy. But when you're designing something, there's always ways to approximate. You can prototype, you can do math, you can do physics, but you never really know exactly how a mechanism will work in real life, right? So iterating on mistakes is always the best way to learn. There's a couple examples I can give. In 2017, I think we cut our intakes like 5 different times. And it made it really easy for us because we had that underlying sketch. So every time we wanted to change something, we changed a couple dimensions and we just cut it again. But every single time we were iterating upon it, we were learning something. And then if we made a mistake, we knew we weren't going to make the mistake in the next iteration. So you can't really, it's really impossible to build something and then put it out on the field and like it's not going to have mistakes, right? There's ways you can approximate how a mechanism will work in real life. You can do prototyping, there's math, there's gears, there's geometry, but you always want to be able to go back, you want to be able to iterate on your mistakes, and you want to be able to learn from them next time, because that's always the most important part of design, in my opinion, is learning, because then you're not going to go back and you're not going to make that same mistake, and next time your mechanism is going to be better. So, that's all. Thank you. And if anyone has any questions, I can go back to any of the slides. I can talk about a couple more examples if you're confused about some of them. Yes?
Do you have any more specific examples of what mechanisms or parts you use multibody parts?
Yeah, I have a bunch. Let me think. So, sorry? Oh, transmissions are always really good because the packaging for a transmission is very tight. A lot of the times, we have a lot of mechanisms on our robots, so our transmissions have a very confined space they need to be in. So then doing multi-body parts help us define transmissions off of what is going to be next to it. So this transmission is going to be next to this massive Arm Gearbox, so how am I supposed to give myself this much room and make everything fit? That's a really, transmission is a good example. I'll give a not good example. So, I don't have a good photo. But in 2017, our gear mech was made out of, it was Lexan, and it held, for most of the season it was passive. So then the human player slid the gear into the gear mech. And then we made that out of a multi-body part, but it wasn't always the best option because it was such a big part. So then changing one dimension made it take forever to load, and that was really annoying as we kept iterating because I think we cut that 7 times. So if you're changing the dimensions one at a time and it's taking forever to load and you have to cut it 7 times, that's just really annoying. That's like not so great. But, yeah.
So when you go to fabricate the multi-body parts, do you like cut it or something?
Oh, I didn't go over that. Can you go back to the slide? That's the multi-body part. Sorry. Okay, that's a very good question. The question was, when you cut multi-body parts on the router, or however you're going to do them, how are you splitting them up? It's a little more. One more forward. One more. Where's the one with the list of parts? Yeah. Okay. It doesn't actually. Okay. So basically, we go through this. Does everyone know what a configuration is? I can go through it real quick. So if you have one gearbox plate and you want you have 2 gearbox plates in one gearbox, right? You want the second gearbox plate to have a hole that's slightly smaller. So instead of making the part over again, you make something called a configuration, which allows you to make 2 separate parts in the same part and modify that second part so that it has that one difference, or maybe 2 differences. So then what we do is we make derived configurations out of this. This is the default part, right? So then you make derived configurations, and then Solidworks actually has a functionality that allows you to delete keep. So you click on a body and you press keep, and then it inserts that into a separate configuration and a derived configuration. So then when we're manufacturing, each part has its own configuration, and that allows us to manufacture upon it. Yeah. That was a really good question. I didn't cover that.